Okay, module number 6. Talking about exploiting vulnerabilities today. As with every chapter, be sure to do the Do I Know This ahead of starting the lecture portion. It should only take you a couple minutes and then you'll be good to go. When looking at the local host, how do we exploit the local host? Well, that starts simply by what protocols or what services are they running. If the host that we're looking at, our target host, is running insecure protocols such as Telnet, Cisco Smart Install, HTTP, SNMP 1 and 2, syslog, IMAP, POP3, FTP, and so on. Any protocol that is insecure, we can see any and everything that's happening across the wire. We're able to see if they transfer any sensitive data. If they log into anything, we'll be able to see the credentials through Wireshark or other tools like TCP dump. Right there off the bat, if they're using an insecure protocol, easy victory. Privilege escalation from within a local system is the process of elevating your rights from a user to an administrator. Usually, this is the focus of the post-exploitation phase. So this happens after you've gained a foothold in the system by going through a vulnerability. You do this in order to maintain your access on the compromised system and move around in the network while still remaining undetected. So this could be normally achieved by logging in as a non-privileged account and then going to an account that has greater authority. You could do something like this in ways like you get onto a Windows machine and you are able to run Mimikatz to get the hashes out for the administrator. Then you can use that hash to log in. You pass the hash into the network like a domain controller and get the get domain admin rights. That would be privilege escalation. It is possible to do that locally from a local user to a local admin, and it's also possible to go from one user to another, from giving a user another group, like the admin group, if they're not added to it. The set UID and set GID can be a program or script where the owner is root set by the SUID. Any of those users will run with super user privileges. So you could do something like this that I have here on the screen to find all the SUIDs and SGIDs on a file system. And here we're specifically looking for anything that matches the 2000 SUID and the 4000 GUID or SGID. SC Linux is a native tool that helps in the situation for access control policies and can handle which apps can run on which resources or what users can do what on a system. This is useful for us as attackers to find out who is on this machine, who has the rights in this machine. Because again, we're probably going to get in through some low-level user. We need to find our way up to root in order to take over the full system. As with most systems, though, they're going to have an insecure implementation of sudo. This is a huge mistake that is often done, where an admin will copy and paste the root privileges and assign them to a user because it's convenient. And as you have heard me repeat in CIS 75, the higher the convenience, the lower the security. It is very convenient to just copy the root privilege and give it to another user. More often than not, you'll find that. So as an attacker, that is a way to go about. Find out that, oh, hey, the user you logged in has these rights, so you have access to get to root pretty easily. This one's going to take a little more explaining. The return to libc attack. This attack actually starts with a buffer overflow. A subroutine will have a return address on a call stack that is replaced by an address of a subroutine that's already present in memory. Normally, this is done to bypass the no execute bit to allow attacker to inject code. So we have our program in memory. It has a return address, but we're going to add this executable. Operating systems that support this no execute bit stack help protect against this very thing from happening. But the non-executable stack cannot prevent a return to libc attack because only executable code is used. Stack smashing, another technique, can prevent or obstruct code execution exploitation because it detects the corruption of the stack and potentially flush out compromised segments. I'll tell you right now, one way around this problem happening is using better programming languages like Rust. Anywho, ASCII armoring can be used to prevent this form of attack. The address of every system library will contain a null byte that you insert in the first bytes of memory. Typically, a few more memory pages, more than 16 megabytes, is also called the ASCII armor region. When this is implemented, an attacker can't place code containing any address for string manipulation, like string copy. So though this doesn't protect the system if an attacker finds a way to overflow null or NLP bytes into the stack, it does start to thwart the way, the buffer overflow, which is the main point of this kind of attack. Is here's the string, here's the whatever code is going to execute. We want the program, instead to return where it's supposed to, we want it to return into system and execute this for us. If possible, if this occurs, then we get the shell through this program. But by adding extra bytes into the stack, it kind of makes it hard to find, harder for an attacker to find where in memory the return statement is. So it's harder to trick the program into running this, whatever they want to run. Does that make sense? Looking at my chats, I see nothing, so I'm thinking everyone's okay. This is one of those things that having some programming knowledge will help understand, or assembly. Okay. Moving on to Windows. cPassword. This was patched in MS14-025 a while ago in 2014. cPassword is a component of Active Directory's group policy that allows admins to set passwords through the group policy. So any user with basic read rights to sysvol can obtain the authentication key and crack it by using things like John the Ripper, Hashcat, or you name it. Now, that shouldn't be a problem anymore. But as I say that, you recall that there are systems out there running old operating systems and unpatched or unpatched. Clear text credentials also exist in Nmap or LDAP. Any event number 2886 and 2887 within Active Directory's log will let you know that Windows domain controllers are receiving credentials in clear text form. You should have, as a defender, you should have a rule in your event IDs, in your SIEM, or any other log management system to just scream bloody murder if you see any event ID 2886 or 2887. This picture, Kerberos. If you thought Kerberos was safe, no, it is not. There is a tool that I have put into the lecture notes from GitHub to attack Kerberos and get access. You can kind of see here the basic premise of the attack, of the request, the ticket, presenting the ticket, and as it goes, we're basically gonna get our way through that whole infrastructure and be able to log in as any user we want. Of course, you also have other tools that you can use locally, like procdump from sysinternals. You can always use Mimikatz and volatility. These are other tools that you can use to obtain user credentials on a live system. Speaking of live systems, even if the computer is on or off, you can, specifically Windows, speaking still, you could use the SAM database. This file is located in the system root, system32, config SAM. If you can get that file copied out, then you have the hashes necessary for that system, both the administrator and any user, any local user who's on that box. At that point, you don't necessarily need to crack the hashes. You could just pass that hash over from one server to another and be able to log in as that user, or you could do both and reverse the hashes, or not reverse, but figure out what the password is and use it to authenticate on like a Kerberos system. Because there's way more ways than one in to into Windows. This picture should have gone first before this picture, but whatever. There's dynamic link library hijacking. Essentially, instead of getting the DLL that the program needs, we tamper with that process and have it load a malicious DIL instead. This is basically interacting with the Windows kernel at that level and getting it to run another DIL instead. It's actually known that Windows programs will look locally within the folder that they're in for any DLLs or DILs. And if they can't find the DIL that they're looking for, they'll go over to the Windows folder. So being able to put the right file in the right, or in this case, the malicious file in the right place can circumvent the whole system, the checks and balances system that is within Windows. Pretty fun stuff. And then this other picture the guy sneaking in. It's supposed to be for the exploitable services, which could be any services that are listening out for the network, and any services that run with system privileges and have read-write access into the drive itself. The typical services that can be used to do this kind of stuff are third-party software. For whatever reason, third-party software vendors who create services tend to make their services so that that process can read and write into the drive. You can take advantage of that and read and write into the drive yourself through that service. Insecure file and folder permissions. It is a complaint of system administrators to ensure all the folders are properly have proper permissions, because they're lazy, because there's a lot of folders that they need to apply to, because it's very granular. Yet, because they choose not to do that well, it opens the door for us as attackers to get in. Because let's face it, it is very easy to just in the Linux world, just do chmod 777 and be done. There, you have full control. Everybody can do what they need, and let's move on with life. That is convenient. Horrible security. Sysadmins should really focus on ensuring that their folders that have sensitive, secret, top secret level information are properly secured, that have the right permissions set to them. Otherwise, it opens the door for attackers like us to gain a foothold, to exfiltrate data and run off, and nobody knows what happened. Lastly, for Windows, group policy. It's there for a reason. Sysadmins and network admins should really take advantage of the group policy. Moving on. Keyloggers. Another way to exploit hosts. Keyloggers can come in many forms. Keyloggers could be kernel-based, gaining root access to hide within the operating system and intercept any and all keystrokes that pass through the kernel. Typically, you can find these as keyboard device drivers, which become pretty hard to combat once they're implemented like that. Because Windows is going to think, oh, this is the proper driver for this keyboard. Why am I going to remove it? And if you roll back, it'll probably keep a copy, so it'll stay there. You can also do Keylogger as an API, compromising the Windows API calls like get async key state, or get foreground window. It is also possible to use a hypervisor to compromise the hypervisor in order to get the keystrokes, since the hypervisor does pass that information into the virtual machine. If you can compromise the hypervisor, you can essentially install a keylogger and be able to see what anybody and everybody types into all the virtual machines. There is also the web form grabbing, recording web browsing on submit events, along with JavaScript, both based on the browser. You can install malicious JavaScript tags to capture key events. And there's also memory injected, where you could do it through a browser, and then it can affect other system functions while the computer is running. I find this all highly fascinating. So many ways that you can get a keylogger installed. And we're not even talking physical keylogger. This is all software based. Another way is a scheduled task. Because how often do you look at your scheduled tasks? Do you check them all the time? Do you routinely see what is in your cron job if you have Linux installed, or your Windows, or your Windows scheduled tasks? Or did you check that one time and then never looked again? And now, as I'm talking about this, you're starting to think, it's been a while since I've checked them. Because the default mindset is, oh, well, I haven't changed them in a while, so they shouldn't be changed, right? It should stay the way it is, yet changes happen. Programs make changes happen in the background. That's kind of what they do. So if you haven't checked your scheduled tasks, just to be sure you don't have a odd new task running in the background, set to maybe exfiltrate data or do post exploitation, do persistence, definitely add that to your list of things to check. As an attacker, know that people don't check those often. So it's probably possible to put a scheduled task in a system to maintain persistence, and it probably won't be detected. If the infrastructure we are testing has virtual machines, well, they probably are trying to find a way to sandbox. Sandboxes, where it could be a virtual machine to test things out or to put malware in to see what happens, they're not foolproof. Malware is, or there are malware that are sophisticated enough to detect that it's a virtual machine and not run, or detect that it's a virtual machine and escape into the real world. So if you create these sandboxes, have a plan B, a kill switch, something like that, because it is possible to work with sophisticated malware that either will get out or find other ways to punish you. You could do things like jailing. This is normally used in mobile devices where apps have a restricted file system namespace and rule-based execution that doesn't allow any untrusted applications to run, hence why we have jailbreaking. There's the rule-based execution, like SE Linux and AppArmor, to control what processes are started, spawned by other apps, or allowed to inject code into the system. VMs, like I said, they are a way to sandbox applications and malware, but again, it's not foolproof. There are ways to sandbox on the native host. For example, putting physical devices on a separate internal network. There are also things like safe computing mode, software fault isolation. Web browsers are supposed to have isolation for their extensions and their plugins, but that doesn't always work. Not too long ago, there was a extension that was found that was leaching data out, and it was supposed to be an ad blocker. HTML5 actually has a sandbox attribute for use within iframes. Java restricts actions of untrusted code. .NET enforces restrictions of untrusted code. Adobe Reader is also supposed to have a sandbox, but we've seen Adobe Reader in the news enough to know that that's not necessarily a working sandbox. And Office, Microsoft Office also has a sandbox for macros, but again, same thing. Um, doesn't always work now, does it? With the addition of DevOps, there has been a lot of activity with things like Docker. Docker is not a virtual machine. It is not a hypervisor. It does allow you to run systems within a container, within a box, but that box is not completely isolated as it is with a hypervisor. That box or container is still connected to the host operating system in a more intimate way than with a hypervisor. While using Docker and other forms of containers are great in the sense of creating little applications to run within these little containers so that they're self-isolated, one of the biggest problems is DevOps folks who just download whatever from like Docker Hub or from GitHub without checking to make sure that it is safe. Most often you find that developers just pull Docker containers and run them without knowing any vulnerabilities that exist in that container. I listed a number of tools that you can use. Snyk, SYNK, is also another tool not added in this list, but also can be used to check for vulnerabilities in these containers so that if a user or a DevOps user downloads a Docker container that has vulnerabilities, it'll let you know so that you don't cause mayhem, or that person doesn't cause mayhem for you on the network. Conversely, it is possible, completely possible, to create a Docker container, put vulnerabilities in it, publish it out to the web, and have people download it. And now you have a way into their system because you created that container. So you know the vulnerabilities. So you know the way that you could use that to make a beachhead and pivot into the network. This could be used in for example, if your target is an organization, this could be used as a supply chain attack. You know what kind of programs they use. You see from research that they're using Docker containers, and you see a specific Docker container that they like to use. So you update it by putting some sort of malware or some sort of backdoor. You wait for them to pull it and run it. And when it runs, it contacts you. And now you have a way in. This happens all the time. This is definitely not something unique. There's a whole nother world with mobile devices. These have to be part of your view. You have to keep these in mind because they're everywhere. They're going nowhere. And users have them and are accessing sensitive data through them. So we need to be familiar. Will a stock Suricata config? Never use a stock config for any tool. Always configure for your network. Always tweak. Never depend on a stock configuration. As both attacker and defender, you always need to tweak your tools for your network. Oh, the first of two, because looking at the market, there's really only two types. Starting with Android, this is the Android software stack. At the lowest level, in red, is the variation Linux kernel with the drivers necessary to operate the device. On top of the kernel, in cyan, is the hardware abstraction layer, defining a standard interface for software to interact with hardware. There are many implementations packaged into a shared library modules that the Android system calls when required, like using a camera, the microphone, speakers. On top of HAL, we have the applications, usually written in Java and compiled in bytecode. Android apps do not have direct access to hardware, with each app ideally running in its own sandbox. The Android runtime contains the maximum number of system resources allocated to apps. The process called Zygote starts up during the Android initialization. This application is a base process that contains all the core libraries the app needs. When launched, there's a socket that opens at dev socket Zygote and listens for connections from local clients. When it receives that connection, it forks a new process, then loads and executes the app-specific code. The HAL is kind of like the API you use when accessing hardware, yes. Android does not implement user accounts in the same way as its cousin. The multi-user support of the Linux kernel extends to the sandbox with a few exceptions. Each app runs under a separate Linux user, isolating it from the rest of the operating system. The unique IDs tend to range in the 10,000 through 19,000. Android applications interact with system services via normal Java methods, method calls that are translated to IPC calls, and then to system calls that run in the background, like network connectivity, the camera, GPS, so on. The Android package kit, which you have seen around as the APK file, is an archive that contains the code and resources required to run the app. It's identical to the original signed application from the developer, and is typically stored at /data app, and then the package name. There are a number of key files that you need to be familiar with if this is the field you want to go into, specifically in pen test, but nonetheless, you should be at least knowledgeable that these exist. I have the complete list in the lecture notes, but you have like the Android manifest, the meta INF, different assets, any libraries, the resources, the REST file. All these things are in every single APK file, or every Android application. The Android application lifetime is controlled by the operating system. Android can kill many processes when it's no longer necessary, or when it needs to reclaim memory to run other applications. It's normally the decision happens based on the state of the user's interaction. Two programs that I would suggest for if you want to dive further into the world of mobile is Android Studio or Genymotion. Now, iOS obviously runs on solely Apple devices. Applications run in restricted environments, isolated from each other at the file system level. Applications are also significantly limited in terms of system API access compared to macOS and other operating systems. This is starting to change as all the operating systems are becoming one in the Mac world. But for now, iOS has more limited API calls compared to the Mac OS. Apple restricts and controls access to the apps that are allowed to run on iOS directly through the App Store. So kind of like Android, the apps are in sandboxes. There is mandatory access controls defining a resource that an app is allowed to access. iOS actually gives very few IPC call options compared to Android, and a uniform hardware integration called the security advantage. Their architecture consists of the hardware security, secure boot, code signing, sandbox, encryption and data protection, and general exploit mitigations. Every iOS has two built-in AES 256-bit keys, the GID and the UID. These keys are included in the application processor and secure enclave during manufacturing. There's no direct way to read these keys with the software or debugging interfaces, just like JTAG. The GID value is shared by all processors in a class of devices that are used to prevent tampering with firmware files. The UID is unique to each device and is used to protect the key hierarchy that is used for device-level system encryption. These are not created during manufacturing, and supposedly Apple can't restore these. The Apple secure boot chain consists of the kernel, the bootloader, the kernel extensions, and baseband firmware. There is an elaborate DRM system to ensure that only Apple-approved code runs on Apple devices. Of course, this doesn't mean that malware can't get through. It happens over and over again where Apple approves a piece of software and goes up on the App Store and it's malicious. And then they have to take it down after everybody screams and yells. The app sandbox is enforced at the kernel level and has a core security feature within the iOS. All third-party apps run under the same user, and only a few system apps or services run as root. Regular apps are confined to their container that has the app's own files and a very limited number of APIs that we mentioned. Access to resources is controlled by the sandbox, and iOS also has the address space layout randomization and the never execute bit to mitigate any code execution attacks. If you didn't know anything about the two, now you know just a bit. This is a whole world. Just like web application has its own world, mobile is its own. For Pen Test Plus, you are not expected to be masters of the Android and iOS, but these things that I covered, you should definitely have an understanding of. It's definitely a heavier test when it comes to things like the web stuff. That's why we spent 2 weeks on it. Versus this, we're talking about it and moving on. Lastly, we have physical security. And not physical security in the sense of doors and man traps, still talking about devices. An attacker with physical attacks to the target system always has an advantage. This is why protecting the building and facilities is critical. So 3 things that could be done, or here I have a picture 4. But you have the cold boot attack, a side channel attack when attacker tries to retrieve encryption keys during a cold reboot. Cold reboot attacks tend to go after data remnants in RAM. There's the serial console debugging, reconnaissance, and tampering. Since it is assumed that if you are in front of the device, you should be authorized to be in front of the device, there's typically no security through that way. So again, if you have horrible physical security and somebody is able to get their way in, then they could essentially be able to get to the system and log in very easily, because it's assumed if you're in front of it, you should be authorized. And then there's also things like JTAG debugging, reconnaissance, to change settings within the box that you are physically on. One of the simple ways is to protect is, of course, having proper physical security and teaching or educating your users to prevent things like tailgating, where somebody tries to get their pull on human strings in order to get in to a system. A typical way that works is a woman pretending to be pregnant and asking to get into the building. That is a very easy way to pull at human heartstrings and get access into the building. Any questions? Yes, it is possible to require a hardware key to decrypt the OS during boot. The question actually becomes, how will you manage that? Because yes, it is possible to do like a YubiKey or a smart card in order to boot. It's totally possible to do that. It's just now, how do you? Because people are going to lose their key. That's just a reality. So you have to have ways to get around that. I don't know if forcing them to tape it would work. But just know that doing something like that sounds great. Oh, yeah, that would be a bad thing. Yeah. Yeah, having these ideas to implement is great on our end. The question always becomes, okay, so what are they going to do? How are they going to screw things up? As an attacker, that's the things you also want to know is how will the user mess this up, because you could use that to your advantage. Any other thoughts? Questions? Okay.